Hey guys, Buildzoid here, and today I'm going to show you a VRM running. Now, this board here that I'm using is, of course, the Asus X417 Prime-Pro. Big thanks to the patrons for funding the purchase of this. And, well, it's a 6-phase, so, and I have a 4-channel oscilloscope, so you can see right now how basically I have 4 PWM signals and 2 of them are missing. Because in a multi-phase VRM, all of your PWM signals are supposed to be evenly spaced relative to each other. And as you can clearly see that's not the case. There's 2 big gaps after the blue one here. Well, there's 2 gaps around the blue one, and those are because those are the 2 phases I don't have hooked up. And in theory, I might find there is a way that I could have multiple PWM signals on one oscilloscope probe or like one channel, but I think this just this is good enough for like just demonstrating some things I wanted to demonstrate. So that's basically what the MOSFETs see. That's not the output of the VRM, but that's what the MOSFETs see right there. And I wanted to today show what you can do with the DG Plus VRM settings. So I'm just going to load optimize defaults here, and before we start doing anything, I'm going to set the CPU to 40, and I'm going to set the VCore to 1.3 volts. And that is way too much VCore for that kind of clock, but I'm just doing that so that the VRM has a fixed voltage target, and we see something that's a lot cleaner than if the VRM has if the power states are running, because then the voltage just keeps fluctuating, and it makes it just makes the waveform it makes the signal really messy, which is correct, but it's just like for the purposes of my demonstration it doesn't work. So yeah, fixed voltage. And VRM is now running completely bone stock. So let's save that and go into Windows. And right now, what's on the oscilloscope is actually not stock. That was a custom configuration that was left over from the last attempt I made at making this video. So while this fires up, also the CPU I'm testing with is a 2700X provided by alza.co.uk. It's on loan to me, so big thanks to them for the chip, because buying a 2700X would actually, make buying more X470 motherboards for testing not an option. The scope here is a Rigol DS1054Z. So, yeah, and thank you patrons for, funding the purchase of an oscilloscope as well. So, there. Now, I have Task Manager opened up, and I wait for the CPU load to hit 0, because ideally I want to have only the yellow PWM signal running, but that's evidently not going to work out. But you can kind of see how basically the phases are dropping in and out of the oscilloscope shot, and that basically indicates that they're being turned on and off. So yeah, it is really messy, and hopefully later on when we change some of the other VRM settings, you'll see a cleaner version of this, but for now this works. So, let's go with that. Now let's run some load on the VRM just to show you what that looks like when the VRM is fully loaded up. And there we go. Now it's running, and you can see how the order in which the PWM signals are going keeps changing all the time. And the reason why it keeps changing is because the voltage controller, so the International Rectifier 35201 that Asus uses here, is basically trying to maintain in this configuration thermal balance between all the phases, while also, of course, maintaining voltage regulation balance on the output side. So basically, it's to prevent VRM hotspots by making sure that whichever phase is hottest is loaded the least. And basically just staggering them in different orders can achieve that kind of thermal balancing. Current balancing is also a thing, but that's like on the stock settings of the motherboard, that's not what the board is going to be doing. Guess we could try see if for a single core load it will run less phases, but in my experience so far, it hasn't done that. Basically, as soon as you do anything more than idle, it'll fire up all the phases. I think with one configuration, I had one situation where it looked like it was running 5-phase or maybe 4-phase mode, because the signals had a very different spacing from what you'd normally see. But yeah, hard, like I've not managed to replicate that. So let's try single core. And, well, you can see that the thermal balancing is doing a lot less work now. So, well, thermal and current balancing, because right now the board is set to prioritize thermal balance, but that doesn't mean it just ignores the current balancing completely. So I think at this point you can see what it's doing, so we'll just cancel the render and start playing with some settings. Also, actually, before we go back to the BIOS, I wanted to point out the switching frequency under full load right here. That's the switching frequency of the VRM. That's 300 kilohertz. So right now, every single phase is being switched on and off at well, the PWM signal driving every phase is running at 300 kilohertz. So, yeah, that's that, which I figured would be kind of cool to see. And, well, we're going to be adjusting that as well. So let's go to the BIOS. And the first thing we're going to do is we're going to play with the phase control. I mean, we could change the switching frequency, but I'm going to start with the phase control mode because I think that one's more interesting. So if we go F7, then we go DigiVRM, and then go power phase control. This right here has a few settings, and we have we have standard, which is phase controlled based on CPU command. Then we have ASUS optimized, which I'm pretty sure looks exactly the same as standard. So right now it was standard, let's try optimized. Which might actually give us better idle, like less phases running at idle, but it might also just not make any difference. I'm not entirely sure that there's a special tuning under that setting. I suspect very heavily that that's just standard again, with a different name. Actually, no, it does seem to be behaving a little bit differently, and everything is currently monochrome because the capture card is going derp. Oh yeah, yeah, you can kind of see the phases dropping out more better right now. And I'm not going to fix the monochromeness and the capture cards derping out, because once I restart the system, that'll be back to normal. So the system's running fine. That's not me screwing something up. That's just the capture card being dumb. I could just unplug it and plug it back in, but that's too much effort. So now if we run an actual workload, it looks basically the same, which is exactly what we would expect, because once you're under a full CPU workload, all of the phases should be running because you're pushing a lot of current. So yeah, that's no surprise that now it's running all the phases. And I wonder if it'll run something different for single. Yeah, it's kind of doing, yeah, it's doing a little bit differently for single core workloads. Yeah, so now we got something that looked kind of like it might have been 5-phase mode, or, you know, some kind of non-even phase count just because of the spacing of the PWM signals. But again, unless I figure out a way to hook up all 6 phases at the same time, it's not gonna be particularly visible. But you can see how the voltage controller basically varies how many phases are running depending on how much work the CPU how much power the CPU requests. Let's stop that again, and nope, and restart. Next, we're gonna put the VRM into extreme mode, which extreme mode forces all the phases to be turned on all the time. And what that does is it basically means you have the best possible voltage regulation under any load condition. The downside is you get a lot worse power efficiency. Like, you produce a lot of unnecessary heat turning on and off your power MOSFETs 300,000 times a second when they're not actually pushing, when the CPU doesn't actually need any significant current, and I just went to the wrong menu. So if we put that, nope, that's the power duty. That's the UT control. We're gonna go with extreme. Also, the T-probe versus the extreme will vary the UT cycle length. Not just the phase running order. To maintain thermal balance. But the thing is, I can't show you the differences in the UT cycle like control because I'd have to somehow correlate it to how much current is going through each phase, and that's really hard to do. So, well, actually, I can't think of a way to do that. So, yeah, we can go with really, really hard to do, because I don't even know how I do it right now. Anyway, let's run Cinebench again. And it looks as usual, you know, all phases running. And then, you know, we come out of load and we still have all phases running, and we can close Cinebench now. We can open up Task Manager, and we can see that the CPU is doing absolutely nothing, and still we have all the phases running. So this is, you know, you get better voltage regulation all the time, everywhere. The downside is you produce a little bit more heat, and I'm saying a little bit more because each of these power stages, by running at all, is going to produce like half a watt of heat if it's just running and pushing a very small amount of current. Of course, you're running potentially 4 phases more than necessary, or 5 phases more than necessary. So that might total up to being like anything from, well, I'm not sure about that 0.5 watt figure. It might be like 0.7. I don't remember the data sheet that well. Especially not that part of it, because I normally deal with like full load currents, not idle. So you might be looking at something like 2 to 4 watts of extra heat output at idle, which, I mean, the VRM doesn't care. And quite frankly, since you're not in a laptop application as a desktop user, I also wouldn't really care either. But, yeah, it is power that you're just kind of wasting on running the VRM when it doesn't need to be, you know, running all its phases. So that's the thing. Let's restart. And finally, we have the manual settings. Now, the thing about the manual settings is I can't actually show you a difference between these because these change how quickly the VRM responds to current draw changes. And I've not managed to like see or notice any kind of like significant difference. Like they all, as far as like if you just watch the oscilloscope, they all look exactly the same. They shed phases at idle and they run all phases at full load. So yeah, but I will demonstrate that they do shed phases. So that's that. And honestly, I would not see a reason why you wouldn't run that at ultra fast. I guess you would lose some power efficiency again. Basically, everything that makes a VRM better at voltage regulation, like adding capacitors, raising switching frequency, running more phases, all of those lower VRM efficiency at low loads. The lower your load and the more components you're running for no good reason, the more power you're wasting. And actually, the capacitors waste power all the time. Like, just from the like the charging and discharging, that every time that happens, they waste power for you in that process. So yeah, that's kind of unfortunate trade-off. Same goes for switching frequency. Like, you crank up the switching frequency and you like your power efficiency just goes down. And yeah, so under full load, it doesn't really make much of a difference, if any. And the rent, well, I'll let it finish. It doesn't take that long. Let's get Task Manager up. Once we hit idle, you can see how the phases are getting dropped off again. So right now we're running in like what looks like two-phase mode, because we have the blue one and the yellow one were, you know, evenly spaced and running at the same time. Right now it seems to have turned off all the phases I actually have on the scope. There we had yellow and pink running at the same time. So yeah, basically you don't run all your phases at idle, and just moving the mouse will actually, well, let's grab a window. There. you can see how the VRM immediately responds to any action I make that puts any amount of load onto the CPU. So, yeah. But if you're just completely doing nothing, the VRM basically shuts down a good chunk of itself. That looks like four-phase mode right now. Anyway, let's get into the BIOS again. And for convenience, let's go F7, iTweaker. I'm going to put the VRM back into extreme mode, and we're going to enable the spread spectrum. Now, it does say disable this setting when overclocking, and there's a reason for that. Let's save and restart. So the thing about having, you know, switching anything is that things that switch produce noise. They produce electromagnetic interference. And the more current you're switching on and off, the more noise you are likely to make. And because of that, there's something called spread spectrum. And the capture card's being derp again. Lovely. But the spread spectrum, so you have spread spectrums for things like the CPU clock. That's why the BCLK is not constant. It floats around a bit to make sure that the CPU isn't producing ungodly, well, not producing more EMI than is allowed by regulations. Similarly, we have the VRM spread spectrum, which you can clearly see what it's doing. It is bouncing the switching frequency up and down, basically. You can see how the switching frequency is going between sort of 300 kilohertz and 450 kilohertz, and because of that, we have this way, like, the PWM signal seems to be getting shorter and longer over and over and over again. And that's entirely to reduce the amount of noise that the VRM is introducing into, like, basically producing. And the thing is, you should turn that off if you want good overclocking performance. But if you have EMI sensitive equipment near the computer, or like if you have some kind of problems with EMI, then you probably want to turn that on. But if you don't, then you want to keep that turned off, because that's what it does. And it basically just does that to the switching frequency. We are currently in you know, all phase mode, so I'm not going to even bother going to full load. I actually could have just gone straight to the BIOS with this setup, because it does this everywhere, which it's supposed to. That's the whole point. Now then, we'll turn that right back off. And we will now play with the switching frequency, which is really self-explanatory. I mean, you set this to, well, first let's start with a baseline of 300, just, you know, back to normal. So that you have, like, a good point of comparison visually. So there we go. that's running all well and good. We press F7, we go to the Digiplus VRM, and now we crank this all the way up to 600. And bam! Now we're running at 500 kilohertz, which is odd. I don't know why this motherboard tends to do that. Like, it'll sometimes, like, I've got it to display 600 kilohertz a few times, so it can do 600 kilohertz. I have no idea why right now we're at 500. Let's try this. 550, and then I'll go back up to 600. There. So now we're doing 550 proper. Or like we're doing 550 plus minus, you know, some amount, because the actual frequency spec for voltage controllers, there's a margin of error on that. So that's not reading perfectly 550 kilohertz because it's not built that, like, it's not meant to be that accurate. I think it's plus minus 10% for switching frequency is the standard, is like the normal tolerance. So yeah, it's not a parameter of voltage controllers that's like super tightly controlled. And now we're doing, hopefully 600. Are we? Yeah, we're doing like yeah, we're just doing just under 600 now, so that's annoying. Oh well. But basically you can see that the PWM signals get higher, you know, frequency. And this has benefits. It lowers your VRM ripple on the output side because your charge and discharge cycle, well, yeah, let's just call it a charge and discharge cycle for the inductors gets shorter. And so the voltage rise and the voltage fall across on the inductor happens for a shorter period of time, so it has a smaller amplitude as a result. And yeah, higher switching frequency gives you so less voltage ripple. It gives you better voltage regulation because there's less ripple, and you also get better transient response because the voltage regulator can respond to a change in load faster because it can update it's updating each phase 600,000 times a second instead of 300,000 times a second. So if there's a big change in current draw suddenly, it can respond to that very, very quickly. Well, about twice as fast as normally because it doesn't, you know, you don't have this, the delay between PWM pulses is half as long. Kinda half as long. It's not literally half as long, but roughly. So yeah, now there is a downside to cranking up your switching frequency like this. It lowers your efficiency because, as I mentioned earlier, did I mention it in this one? I've done so many takes at this point, I can't remember. But cranking up the switching frequency lowers your VRM efficiency because turning MOSFETs on and off, oh yeah, I did mention that, costs power. And turning them on and off faster means you waste more power. Now, the cool thing is, depending on how the VRM is designed, you can actually design it for like higher switching frequencies or lower switching frequencies. And there's things like, say, the power stages on this motherboard, which are International Rectifier 3553s. The difference between running them at like 500 kilohertz and 300 kilohertz is like 3% in power dissipation, which means if at 500 kilohertz, these for 10 amps, 500 kilohertz, these produce, I think it's like 1.2 watts of heat. Then for 300 kilohertz, 10 amps, they will produce 1.17. You know, they'll produce basically the same amount of heat anyway. So there's no reason to not run them. So in my opinion, there's no reason to not run them at, say, 500 kilohertz or 400 kilohertz. I'm actually kind of surprised that Asus runs this VRM at 300 kilohertz, though that might have something to do with the inductors they chose, as higher switching frequencies do potentially lead to higher like switching losses on the inductors themselves. But as far as the MOSFETs are concerned, you know, 500 kilohertz is no problem. Now, 600 kilohertz compared to 500 kilohertz, on the other hand, does actually make a relatively significant increase in power consumption just because of the way these MOSFETs from International Rectifier are tuned, and they work, basically they're designed to run at 500 kilohertz. Past that, they get really inefficient really, really fast, and below that, they don't get a whole lot more efficient. But yeah, so that's kind of the situation with the switching frequency. You basically lose some VRM efficiency, and you gain some voltage regulation, which can, in theory, translate into more better overclocking performance. So you should be able to hit higher clocks at lower voltage, or the same clocks at lower voltage, or you know, that kind of thing, or potentially higher clocks at higher voltage. Like it can go in many ways. But the thing is, there's also a point of diminishing returns, and basically if this VRM is doing perfectly well at keeping you within, like, if the difference between 300 kilohertz switching frequency and 600 kilohertz switching frequency was 5 millivolts peak to peak ripple, you're not going to notice. Like, it's going to be like your V-core is going to go by, like, down by, like, 5 millivolts for your given overclock, which is just, like, you're not going to notice. I mean, I'm pretty sure AMD's voltage standard doesn't even do 5 millivolt steps, which it doesn't. Which I've just realized you can't see. But AMD's voltage, like, yeah. AMD's voltage controllers, by spec, don't even do 5 millivolt voltage increments. So if you knock off 5 millivolts peak to peak, actually, if you knocked off 5 millivolts peak to peak, it would be half of that, because your minimum voltage would only get lifted up by half. So, yeah, basically there's a good chance that cranking the switching frequency way up there will, well, what it'll definitely do is lower your VRM efficiency. What it might do is improve your overclocking potential, but it's depending on how good the motherboard you're on is to start with. Like, if you have a lot of phases, you don't need a super high switching frequency, because there's a lot of phases. If you have very few phases, then a high switching frequency can compensate for the phase count, because you shorten the time between each PWM pulse. But basically, there's, like, if, like, on this motherboard, I would not be surprised if at 600 kilohertz the board clocks exactly the same as if the VRM was at 300 kilohertz. So yeah, here it would make no sense at all to actually change the switching frequency. Now, there are some applications, some situations where cranking the switching frequency way up there makes sense, but usually you're talking about extreme overclocking with very, very high voltages, very, very high currents, not, you know, daily systems doing daily overclocks. So, yeah, that's it for the video. Thank you for watching. Like, share, subscribe, and I hope you found this all interesting. Leave a comment down in the, you know, comment or any questions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, then I have a Patreon, a PayPal, and there's t-shirts you can buy. You can find all of that down in the description. And one last big thanks to, you know, the patrons for funding things like the oscilloscope, the motherboard, the case that this is actually all sitting in, and also thank you to alza.co.uk for providing the 2700X that I'm using here. And yeah, that's it. So I gotta go hit that stop button now.